Hi, my name is Dan Berwick. I'm going to talk to you today about the basal ganglia. The basal ganglia is the system of brain structures that we use when we want to make a voluntary movement. I'm going to walk you through the system and introduce you to its various component parts. Then, I'm going to talk to you about Parkinson's disease, which is a disease primarily caused by the disruption of the basal ganglia. So we'll start with the anatomy of the basal ganglia. On the screen at the moment are four brain structures that are indisputably part of this system. The striatum, two parts of the globus pallidus, the external globus pallidus and internal globus pallidus, and the subthalamic nucleus. However, to make sense of the system from any functional point of view, we need to include a few other parts of the brain. Very importantly, we have to include the substantia nigra. As we'll find out, it's a very important player in the system. We should also include the thalamus. The thalamus is part of the output of this system, and also the cortex. The cortex has two roles within the basal ganglia system. So firstly, it's the source of input into the system. So information from our senses is fed into the striatum and the substantia nigra. And then at the end, the supplementary motor area of the cortex is the final destination of the transfer of information within the system. It's the connection, the output from the thalamus. So I've introduced the structures. The question is, how do they fit together? Well, that's depicted here. This is a very oversimplified representation, just showing you the flow of information in an anti-clockwise direction. From the cortex, by striatum and substantia nigra. From the striatum, the flow of information splits into two pathways, reconverging at the internal globus pallidus. Information is relayed to the thalamus and back to the cortex. So this divergence in the flow of information after the striatum that comes back together again at the internal globus pallidus is quite a critical detail. I think it's important that you understand the distinction between these two branches. The first, indicated here, which is a direct connection between the striatum and the internal globus pallidus, is called the direct pathway. The second branch is, unsurprisingly, called the indirect pathway. Now, this is a very simplified diagram. Of course, we're dealing with neurons here. And neurons have two basic types of connection. They have excitatory and inhibitory connections. And in further diagrams, I'm going to use these arrows to represent these two types of connection. Also, to show you when the structure really has become activated, I'm going to put a blue halo around it. That way you know what's active and what's not. Okay, so we're going to start with what the basal ganglia are doing at rest. So in the absence of any desire to move. This is quite simple really. There are two structures which are considered to be tonically active. That is to say they're active in the absence of any stimulus. That's the two parts of the globus pallidus. And what do these do? Well, the external globus pallidus projects inhibitory neurons to the subthalamic nucleus and to the internal globus pallidus. The GPI, the internal globus pallidus, has a projection to the thalamus. And when both of these structures are tonically active like this, the net result is that the thalamus is inhibited, there's no excitation of the cortex, and there's no movement. Okay, so that's what happens at rest. But what about when we want to move, when we want to make a voluntary movement? Well, to help the explanation, we're going to break the system down a bit. And initially, we're just going to focus on these first three components of the system: the cortex, the striatum, and the substantia nigra. So as mentioned, the input to the system comes from the cortex, and it leads to an excitation of the striatum. This in turn leads to the activation of downstream pathways, the so-called direct and indirect pathways. As depicted here, we have those immediate connections, axonal projections from the striatum, and in both cases these are actually inhibitory connections. In parallel with activation of the striatum, the cortex also excites the substantia nigra, and as we'll see, the substantia nigra has a really interesting role to play. So the first thing that the substantia nigra does to the pathway is it provides an additional excitatory input to the direct pathway. Thus, we have excitation from both the cortex and the substantia nigra, leading to a strong activation of the direct pathway. By contrast, the substantia nigra provides an input to the indirect pathway that's actually inhibitory. And thus, the indirect pathway has excitation from the cortex and inhibition from the substantia nigra, meaning it's far less activated. This differing effect of the substantia nigra on the two pathways is actually quite remarkable because it's achieved entirely by the same neurotransmitter, in this case dopamine. And this selectivity of outcome is because the neurons in the two different pathways express different types of dopamine receptor. Anyhow, the output of this system is clear. When we want to make a voluntary movement, we get strong activation of the direct pathway with only a weak activation of the indirect pathway. So we've seen what happens to the output of the striatum when we want to make a voluntary movement. We get a strong activation of the direct pathway, but only a relatively weak activation of the indirect pathway. And that's actually quite important because the direct pathway is considered to be pro-movement, whereas the indirect pathway is thought of as the brake on this mechanism. It's anti-movement. So having established this, let's integrate the information back into the entire basal ganglia system and look to see how this change in strength in the two pathways will affect the output of the system. Well, quite clearly, we can see that by activating the direct pathway strongly, we're getting a greater inhibition of the internal globus pallidus. In contrast, the effect on the indirect pathway is a little bit more complicated, so we'll go through that step by step. Now, at rest, as you will remember, the external globus pallidus is active, but now it has a mild inhibitory input from the striatum, meaning that this structure is now less active. Because it's less active, there's less inhibition of the subthalamic nucleus, leading to some excitation of the internal globus pallidus. At the same time, the decreased activity from the external globus pallidus means we have less inhibition of the internal globus pallidus. So let's sum together these inputs to the internal globus pallidus. We now have an excitation from the subthalamic nucleus, but it's coupled with some inhibition from the external globus pallidus and a very strong inhibition via the direct pathway. The result? The direct pathway has dominated, and now we have less activity in the internal globus pallidus. Again, this was active tonically, and now it's essentially switched off, meaning that there's no inhibition of the thalamus. We've released this handbrake on the thalamus, and it's active. It can excite the motor cortex, and voluntary movement can occur. So we've covered what happens in the basal ganglia when we want to make a voluntary movement. But what about in people with Parkinson's disease? Now, Parkinson's disease is a movement disorder where one of the major symptoms is bradykinesia or akinesia. That's little movement or no movement at all. At the cellular level, the neurodegeneration seen in Parkinson's disease is caused by the progressive loss of the dopaminergic neurons within the substantia nigra. And we can, by looking at our diagram here, we can predict what's going to happen and how it will cause these symptoms of bradykinesia. So we lose the substantia nigra, we lose the input of dopamine on the direct and indirect pathways. The direct pathway has now lost an excitatory input, meaning it's less active. By contrast, the indirect pathway has lost an inhibitory input and is now more active. So, in the indirect pathway now, on the external globus pallidus, we have more inhibition, so this structure is now essentially off. We have, because of that, no inhibition of the subthalamic nucleus of the internal globus pallidus. The subthalamic nucleus, because it's lost its inhibition, is now very active, and we get a strong excitation of the internal globus pallidus. So the situation here is clearly very different to in a healthy individual. Whereas before we had a strong inhibition of the internal globus pallidus via the direct pathway, now it's greatly reduced, and instead we also have a strong excitation from the subthalamic nucleus. The sum of these two inputs is that the internal globus pallidus is now strongly active, leading to an inhibition of the thalamus. The result of this is the thalamus is less active, providing less excitation of the supplementary motor area, which in turn leads to difficulty in initiating voluntary movements, which is essentially bradykinesia. And lastly, I'd just like to thank you all very much for being patient and listening to me. I hope you've learnt something. Thank you.